All right, welcome. We're going to start the second part of Chapter 6, which is called Frames and Machines. The first problem we're going to look at involves simple machines, pulleys. And just note that for the most part, the problems you see, what differentiates this between Chapter 6 and Chapter 5, the problems here in this chapter tend to be a little more sophisticated. They usually require more than one free body diagram to solve the problem. Or if there's only one free body diagram, there may be more complicated geometries that people struggle with. So just a step up, but conceptually no different from Chapter 5. All right, so getting on to this first problem, we have a pulley system, and so we're pulling on the rope here, and the question is what is the tension in this rope and what is the tension in that rope to support this 100 pounds. Now in a lot of our problems we tend to have the pulleys be massless. The rope is always massless, as it is in this case, but in this case we actually have the various pulleys actually have weight. They're 10 pounds each, and we have their radius here. All right, so and we'll note that we're pulling on this here, and then we're asked for the tension there. And we'll allow that. Actually, this should be an obvious answer, but we will allow this for this problem. So let's go into the first free body diagram. If I was looking at this problem, I would start right here, pulley D. So we have the whole idea when you do free body diagrams is you cut away structure and replace them with the force and moment as required. Now, this is just a pulley hanging by a string. That's just the force in the string. So there's no moment. It's just boom. Cut the rope, put in an arrow for the force. This is the force on the string, so that is kind of what it is. And then here we cut the string and replace it with the tension. And then this 10 pounds is simply the weight of the pulley. Now, if we look at this thing, if we sum the moments about the center of this pulley, the 10 and the T2 don't do anything. And we're knowing that this is at equilibrium. That tells us since P times the radius equals T times the radius, you must have the moments matching, which basically tells you the tension in the rope is equal to how hard you pull in the rope, which is brutally obvious, but we're just making this a teaching point for this problem, just for those that aren't aware of that. So, bam. We have the same tension, so we still haven't figured out what P or T1 is, but they are the same, and we figure out P will have the tension in the rope. Okay, we're done with that. So if I look at this now, I'll just sum forces in the Y. I have a T2 going up. I have two P's. This is equal to P, so I'll just go with P. Two P's going down minus 10 equals 0. Now I'm going to go to this next pulley. All right. And so T2 is here. It goes up and over. So that's a T2 here in the center. And then that would become a P there and a P there. And we're ready to go. So we have T2 plus 2P minus 110 equals 0. And so if we look at this, it's actually, hopefully you can see this is really straightforward to work with. So we've got 2t minus 2p, t2 minus 2p minus 10 equals 0, and then we have the other one. So two equations, two unknowns. I will let you solve the problem, but it works out. You get p is 25 pounds, t2 is 60 pounds for the tension. So that would be tension in B is 60 pounds. And there we are. First problem. Now we're going to, oftentimes when we start a section, the first problem is pretty straightforward. So we'll go to something a little more involved. Okay, and a tad realistic. So one of the things people in trucking will have to do is look at how do they place their load to minimize the loads in the axles. That's really what's being asked here. Okay? And so we have a trailer here. Here's the center of the trailer. It weighs 7,000 pounds. So we have a free body diagram for the tractor and a free body diagram for the trailer. So here's the weight, 7,000 pounds. And if we look here, so relative to the pin, this is 13 feet back. From 7,000 to Q, that's 12 feet. We'll use these numbers later. The cab weight is 6,000 pounds. That's happening right along here. So we have 4, 6, 3 there. We can use them later. And there's the 2,000 pound load Q. That's going to be some distance from C. All right? And the maximum axle load, we're told, is 5,500. How would we solve this? Well, my approach would be to start with A. Why? Because I generally do problems left to right. You could start with C, you could start with B. This is no problem. But I'm going to start with A, as I noted here. So what I'm going to do is start with A and figure out what then B and C and the placement and all that good stuff. All right? So let's figure these things out. So if A is 5,500, what I'll do now is I will take the moments at B. That will allow me to solve for F pin. Then I can solve some forces in the Y and get By straight away. So summing moments at B, we come up with. So let's see. This is now 5,500. 13 away. That's going clockwise. Minus 5,500 times 13. That's plus 6,000 times 9 plus F pin times 3. Okay. And we got to set that equal to 0. Solve for F pin. And one would come up with 5,833 pounds. All right. If this is 5,833 pounds and this is 5,500, so we'd have 5,500 minus 6,000 minus 5,883 plus By. If you solve for By, I'll just write it on top, you would come up with 6,333. We're over our axle limit. Can't happen. Or at least we don't want it to happen. All right. So never mind on that one. So that's not even a viable option. So now we'll just move on. We'll say, well, let By equals 0, not 0, 5,500. All right. And so if this is 5,500, we take the moments there, solve for F pin, sum forces in the Y, and make sure that the cab is good. So summing moments at A equal to 0. We get 6,000 minus 6,000 times 4 minus F pin times 10. Make sure I'm on the right track here. Yep. Plus 5,500 times 13. Set it equal to 0. Come up with F pin is 4,750. And if you sum forces in the Y, you wind up with AY is 5,250. So that's good. We don't have any problems here. All right. So given that F pin is 4,750, all right, we need this to be stable. So we're going to ask the question, where do we have to place the load? Okay, can we place the load in a way so that the some of the moments are 0? And so we'll make that happen. So summing the moments at C, let's see, F pin is 4,750. It's 25 away, and that looks incredibly clockwise. 4,750, 25 minus or plus. This is going the other way. 7,000 times 12 plus 2,000 times Q. And so we come up with Q is 17 point, let me move that up, 4 feet. All right, so to get the load properly balanced here, for 4750, we want this thing more over here. So load's going to be out there somewhere. No problem. So that placement does work. So now we'll just say, since we know that works, if you sum forces in the y, set that equal to 0. 4750 minus 7 minus 2. I'll just do an arrow. You can check it. CY is 4250 for that placement. Awesome. All right. So now we'll go and do this one more time. Now we'll say let CY be 5500. And so what we need to do is find the if the CY is 5500, let's see if we sum forces in the y. We have our F pin minus 7,000 minus 2,000 plus 5,500 equals 0. We'd get F pin is 3,500. All right, no problem there. But what's the positioning associated with that? Summing moments at C. So we would have minus 3,500 times 25, plus 7,000 times 12 plus 2,000 times Q equals 0. Come up with Q is 1.75 feet. All right. Now, we still need to check what the loads are here. Now, what I'd note here is we had a pin of 4750 and a pin of 5800. This is 35, so there's no way these are going to be over 5500, but we'll just go through the math just for the sake of it. If I sum the moments at A, so we're going to take the moments at A. Let's just move this up so you can see this here. So to finish this off, again, this is lower than the pins on the others, so this has got to work out. But if we sum the moments at A, where this pin is 3,500, I'll sum the moments at A. That'll tell me what B is and what so on and so forth. So we have minus 6,000 times 4 minus F pin, which is 3,500 times 10 plus BY times 13. Set that equal to 0, and you would come up with BY is 4,538 pounds. Summing the forces in the Y, AY is 4,962 pounds. Both well in line, and the problem. We now have, this is 1.75, that's 17.4, so anywhere in between would work. And that's all for this video. We have, I think, 5 more problems left to this section of Chapter 6. Bye for now.